Hi, everyone. So my name is Daniel Katz, and I'm a principal researcher at Symantec Research Labs. I really wish that these presentations were like DEF CON, where the first time you present, you have to take a shot on stage. Because I'm a little bit nervous, and I think that that would help. So at Symantec Research Labs, we use Python all the time for data analysis. And I'm going to show you a few ways at which we use Python to catch malicious actors. Of course, this presentation was put together not by just me, but with my colleague Kevin Roundy and many, many others whose projects I have ungraciously stolen. So just very quickly about me. I usually look like this, but right now I look like this. And I did a Bachelor of Science and a Master's at U of T in the Systems group. I started working at Symantec Research Labs in 2016, working on cloud security and big data pipelines, but now I've migrated to answering the central question. How do humans interact with technology? What is our relationship with technology, and how can we leverage that to keep people safe? So a little bit about Symantec Research Labs. It's Symantec's core research group, and we work on problems both practical and theoretical. We collaborate with university research a lot, and we take PhD candidates as interns. So as a brief example, I am contractually obligated to give this plug, by the way. Here are a list of our papers accepted in 2018, highlighted one I contributed to. These are just the ones in 2018 so far. All right, so let's talk about Jupyter. Hands up if you know about Jupyter notebooks. Wow, okay. I feel that this portion of the talk can be largely ignored then, but I just wanted to show you some stuff. So some data landed on my desk, and I want to show you what is the real-life process by which research is conducted. So as you know, Jupyter notebooks are this interactive environment that works within the browser. It can show inline visualizations, equations, markdown, amazing inline support for pandas. You can export them. They're beautiful. You can share them with other researchers so they can replicate your work. They're basically a unicorn. And they were quite rightly awarded the ACM System Software Award last year. Jupyter Labs is the next generation of Jupyter notebooks. The GA was in February 2018, and right now it's still 0 point, but it's very, very usable. It offers quite a few features over Jupyter notebooks, such as the notebooks are grouped, there's some drag and drop, you can collect cells. So if Jupyter notebooks are a unicorn, then Jupyter Lab is like a unicorn wearing a top hat with another smaller unicorn inside. So let's talk about the first project of the day. It's about some data that landed on my desk through quite accidental reasons with the following people as collaborators. So if you're a Chi 2019 reviewer, please leave the room because this is currently under submission to Chi, which is an academic conference on computer and human interaction. All right, no one? Fantastic. All right, so here's how research happens. Basically, I get an email like this. It's from a friend in the Norton group, and it says, "Dear Daniel and co, I saw this data. I don't know what to make of it, but it seems interesting. What do you think?" And so immediately, when I see emails like this, my eyes light up, and I feel all fuzzy, and I bring out the IPython notebook. By the way, I should note that while this is an attachment, it has been anonymized, so my colleagues are very responsible. I'm also contractually obligated to say that. All right, so how does this look like? We boot up our IPython notebook, or our Jupyter Lab console, and go through it. We're like, okay, so let's bring out pandas. Let's open it up. Okay, we get an error. this is extremely typical in these circumstances, and it's a whoopsie. Because a lot of the time, the data is just not meant for Python consumption, so you have to do some clever things. And now we can read it. So we immediately see that the data has some interesting elements, like month, case ID, and a problem description, plus product name. So maybe we want to explore the data a little bit. Let's take a subset of the columns. We can do that. We can see that we get a wide variety of correct-looking records. Can take a look at the size of it, how many null entries, how many empty entries for this problem description. By the way, this problem description being quite interesting in and of itself, I would love to show you, but I can't. So now we start with games like, when we look at the problem description, perhaps it's in different languages. And when you subsample the data, you can see that that's the case. So why don't we detect the language? There's a package for that. Install it, run it, and do this group by, which is taking a while, apparently. There we go. So we can see that by far we have the most entries in English, but we have some French, some German, some Spanish, and a handful of other languages. But it's great because my native language is English, and we have over 1,000 English cases. It's enough to work with for now. Then we look at what is the timeline of the data that we're dealing with, and do it in the following way. And I want to note that a lot of the times in practice, you're going to get data with errors. Noisy data is 100% probable. And you always have to validate your assumptions about what the state of the data is. So when you see something like this, where the month is universally one date, you start to have weird feelings, right? Maybe the data isn't clean. Maybe that's something that you need to follow up on. And the questions are, okay, well, what about the source database? Is its data right? These are the sorts of questions that you should be asking yourself as a data scientist. So when you start looking through the data, you're like, okay, well, maybe the problem descriptions have URLs. And what you want to do is you want to extract those URLs. So how do you do that? Well, there's no module for that. So what do? You Google it, right? And you get some Stack Overflow link, and someone has posted some mysterious-looking code. You look at this regular expression, and put your hands up if you think that this regular expression looks right to detect URLs. Sorry, this one right here. Well then, it looks great, right? Obviously, as with most of these things, it is impossible to tell at first blush, is this even right or not? So the first thing that I would do before trying to run it on every single string is maybe test it with some annoying little case like this, and suddenly it turns out that the empty string isn't handled so well. So you write your own wrapper around it. You make sure that it handles stuff sanely, and then you can apply it to your problem description and get some results. And here, I can follow this up with, okay, what is the nature of these URLs? Can I run them through some semantic internal systems and get more information about them? This is already something that I've learned from the data by going through it for about, 3 minutes? And finally, I want to get a sense of what operating systems these users are running. I saw an operating system field. Let's take a look at that. So, all right, so we have some operating systems, and we see that largely it's Windows. But if you look closely, you'll see that it's kind of not normalized. There's some Windows, Mac OS 10 versions are broken up, and it's not really clear why. So these are other data quality issues that you want to be cognizant of. And so you write some little script, and suddenly you normalize them, and then you can inline plot them. Sorry. Like that. It's always good to be changing your code on the fly, right? So you can see that I adore IPython notebooks. In about 5 minutes worth of effort, we've really gained an insight into what kind of data we're dealing with. All So we started off with that data, and this is basically what I did. So I sampled some chats, I read them, and did some data analysis. And then I thought, I wonder what I can do with this data. So start out with some questions. Maybe we can use the data to predict attack trends. I should have said that this data comes from customer support chats for the Norton product. Perhaps we can use it to identify bugs in our product. Are there common misconceptions among customers? Is there something that we can use to improve the product or work on user education? And then how do you address these questions? How do you answer them when you're a busy person, you're working on other things? Well, meet Mahmoud. Mahmoud was an intern that I hired, or that we hired to work on this problem. So the answer is you hire an intern. And Mahmoud, aside from being a great person, is also an amazing researcher. And we had this idea of, okay, we have these user perceptions of what the issue is, but we don't have the final diagnosis. Was the user right? So we pulled in expert information from other database, but it turns out that they're just kind of notes. They're not in any standard format. We need labels. So how do we get labels? Well, we pick the 4 researchers who are working on the project, and then we say, all right, we will divide the work equally. We will provide labels. But then I say, I'm a little bit busy at the moment, and I'm not sure if I can manually go through all these chats. So the remaining 3 researchers manually labeled the data set, and this is what I call productivity. So here are some preliminary results from the paper. Basically what we found is that if you're looking along the cardinal diagonal, you see that there's a large alignment between what the customers believe the problem is and what the experts say it is. So red means a strong agreement. However, in certain cases, there is not a strong agreement between what the customer thinks and what the expert thinks. And we found that generally, that is the case for scams. So they're specifically leveraging this misconceptions in the way that users interact with technology in order to scam them, to take their money, to get them to perform actions that they wouldn't normally do. So we had this next idea. Can we write a classifier from just the user problem statement to predict what type of issue they have automatically and then route them to a specialist right away? So we turn to doc2vec, which is a method of working with unstructured data. So you have a corpus of text, and you are distilling what are the keywords in this text into a feature vector. Then trained a classifier. And my takeaway from this and from the research that I've done so far is you want to start simple. Your first instinct may be to crack out TensorFlow or Keras and train a very deep neural net, but in practice, that's not really necessary, and it overcomplicates the issue because you can get away with something like a simple logistic regression from sklearn, and you can hit very high percentages like we did. So finally, let's talk about scaling this thing. It turns out that you don't have to use Jupyter notebooks with only Python. You can use PySpark. And you can actually run Jupyter Notebook code remotely while writing it locally using a project called Livy. And this allows you, in our case, we have a giant data warehouse, many billions of records, and you can run your query in just a couple of hours. So what are the lessons? The first lesson from manually going through the chat is that users who are less certain about what their problem is are more often correct, which I find a very Zen-like and philosophical lesson to draw from this. Second is, as I mentioned before, attackers will leverage user uncertainty on purpose to pull off scams. And if we go back to our research questions, it turns out that we can actually do all 3 of these. All right, let's talk about another project. This one is on Stalkerware. So for those, and this is in collaboration with Cornell and with the mobile team at Symantec. For those of you who are thinking, I was promised catching bad guys. Where are the bad guys? We're coming to them. All right, so Stalkerware is not a particularly happy thing. They are apps that are specifically designed to spy on intimate partners. Sometimes they're not marketed that way, but when you go deep within the page to download the app, that is, in fact, what they're for. Sometimes they're what we call dual-use app, and they're heavily linked to violence and other acts of aggression against intimate partners, which we at Symantec are not a fan of. So what's the traditional way of detecting mobile malware or any kind of malware? And we start out with some static features like information from the manifest, information about the author, signer info, dex file, stuff like that. Then you loop in some dynamic analysis, so taint tracking, looking at how data moves from the user to the network. And we create in-memory signatures, which hit strings and other behaviors. And then we have hybrid approaches, which look for obfuscation and attempt to force the app to unpack and reveal its true behavior before doing the a priori methods that we mentioned, with some anti-sandbox detection thrown in. So this is the traditional method, and this is something that Symantec has been doing for years, and it's quite effective. But we thought, what if we took a slightly different approach? So we had this idea from a project that we worked on with generic incidents. The idea is to model the ecosystem as a bipartite graph. Raise your hands if you know what a bipartite graph is. Raise your hands if you know what a bipartite graph is by looking at the picture of the bipartite graph. Okay, so the idea of a bipartite graph is you have two sets of nodes, A on the left, B on the right, and there are no links within a set of nodes. There are no links in the set of A, and there are no links within the set of B. All the links exist between set A and set B. Okay. Now, how many of you know what a bipartite graph is? Perfect. We're making progress. So how do you model this ecosystem as a bipartite graph? On the left in your set A, you can use the devices. And on set B, you can use apps. So you create a link every time an app is found on a particular device. So what does this graph allow us to do? Well, it allows us to spot correlations between devices and applications, and how often do they co-occur. In particular, the intuition is the following. We have this bipartite graph of devices and applications. And some applications we know are evil. We know they're malicious. Other applications, we know they're fine. And we say, we have some set of applications that we don't have any information on. Can we use this graph to gain information about them? So, by the way, this is drawn with an excellent NetworkX graphing package in Jupyter notebooks. So what we do is we can propagate this idea of confidence along the edges. And we can start coloring the devices as likely to contain malicious applications or not likely to contain the malicious applications. And then those can feed back into applications, right? What is the probability that this application is malicious given that it was found on a given device? And so I'm not sure how clear the colors are, but the top one that was previously unknown, we see it's kind of a dirty brown, which implies that it's not so good, whereas A2 is probably fine because it's kind of a clear green. And you can imagine that you would perform this procedure over many, many rounds. So why would this even work? Like, why is this probably going to work? Well, the intuition here is honestly not very clear, but I would say it goes like this. Stalkers are terrible and lazy people, and they're also paranoid. And they're very likely to install multiple applications because they don't trust that just one will work. They may try one application for a while and then install another one. Or they may have redundancies in place, or they may have applications which monitor for two different things. Does it work in practice is really the hallmark of this approach. And right now, we have some promising early results, which seem to indicate that yes, it does work in practice. As an aside, you would not believe how obvious it is for a lot of these dual-use applications when you look inside the binary that it is really geared towards this idea of stalker, because the app's names will themselves contain the word stalker. You're looking at the packages in APK, and it's like something.stalker.something.something. Like, yes, you are a legitimate application. All right. So, the results and conclusions from this section are that terrible people use Stalkerware, and terrible people make Stalkerware, and together they create this ecosystem which it makes me very happy that we can disrupt. And if you are working on these dual-use apps, please stop. It's hurting real people. So we're working on this project in collaboration with Cornell University, and we hope to publicize the findings widely in order to help shelters for against intimate partner violence, such that they are able to correctly identify these applications and remove them from the phones of people who are affected, such that the people who are affected are no longer at risk. And to wrap up, you can see that people have very complex relationships with computers. They use them to try to feel secure about the world. They use them to try to understand the world. They use them to try to control those around them, and they use them to try to trick people. And I find this relationship endlessly fascinating, and I think that it's worthy of study. The second point is, I don't like it when people with power take advantage of vulnerable people, and it makes me very happy to be in a position to stop that, both with identifying scams and identifying malware and identifying stalkerware and all the other things that I do. And finally, Python is an incredible language, but it has far to go. We at SRL love Python, and we hope to continue this collaboration. That concludes my talk, but I really wanted to take questions at the end of it. You can find me on all these places. Thank you.
Okay, are there any questions? Anyone?
No.
Okay.
Right.
If you have questions
If you have questions, you can find me afterwards. In this case, I have planned for this. I have 5 minutes at the end, and I will give some color to this final slide, which is, I think Python is an incredible language, but it has far to go, because while Python has all these amazing features of, it's got a great ecosystem, it's got an amazing community, it has all these modules, there are severe gaps which keep it from being as great as it could be. So consider this my airing of grievances. The first one is that when you're in a position where you're running a very long-running job, and then you have just a little bit of code after the job. Let's say you run a PySpark job, and it takes an hour, takes 5 hours. And then you have some code which will maybe checkpoint or save preliminary results. What happens if you have a syntax error in that second line of code? Python will very happily run your PySpark job for an hour or 5 hours, and then not save your preliminary results and crash on your second line. I think that this is maybe the biggest problem with respect to Python and scientific computing, and something that I would hope that the Python community works on, because it feels like a language feature which should be core, but is missing, especially as we move towards long-running machine learning jobs, long-running PySpark jobs, long-running data analysis in this fairly complex way. The second is that how many of you are familiar with MyPy? So about a third. MyPy is an incredible tool which allows you to perform some degree of static type checking in Python by use of Python 3 type annotations. And these are incredibly useful for programs written in Python which are running in production just to make sure that everything is kind of going okay. However, what is missing from this? First, it's not a first-class citizen of the language, and it should be. And secondly, if you are using MyPy, wouldn't you like the assertions to be auto-generated? Is that not something that should be part of the language? There's something to think about. And with that, I again conclude my talk. Thank you very much.